So this is our final project. We decided to simulate MTD bus stops as an undirected graph with distances between each bus stop as weights. My name is Neo.
My name is Michael.
I'm Rohan.
And I'm Calvin.
Great. So our group knew that we wanted to explore shortest path algorithms. While we were brainstorming what data sets to use to implement these algorithms, we initially thought of something that was pixel based. Initially we had thought of finding the shortest path between two different pixels on a certain image. In this case, the image that's on the screen. But we soon realized that in order to implement a lot of like the shortest path algorithms like Dijkstra's algorithm or A star, we needed to be able to weight the edges of our graph. An image like this, it wasn't super well represented by a graph, and we wouldn't really be able to weight pixels. Instead, we started exploring other common graph implementations. We brainstormed flight paths between airports, and we decided on doing something a little bit more centric to Champaign-Urbana. We took MTD bus routes, and we tried to find, and we implemented shortest paths between two bus stops in Urbana-Champaign. This is how our data set is set up. And so all of this is sourced from the MTD website, developer tools on the MTD website. So each entry in this data set is an edge in our graph. And so the first entry is the source stop, and then the latitude and longitude associated with that stop, the destination stop, and then the location associated with that destination. And then the route ID is whatever bus number it is, whether that be the 1 or the 22 or the 13. We have a bunch of edges that are sourced from the MTD website. Those comprise the edges of our graph, and then our nodes are each individual stop. We decided to write an MTD class to parse the data and to serve as wrapper functions for our shortest path algorithms. We have a function here called construct graph. And so all that does is it parses the data set line by line, and it categorizes the data based on our delimiter. So in case anyone wanted to add information into the data set, you could do it following the same schema, and it would be added to the graph whenever this function is called. And we just use a hash map to determine if a vertex already exists in the graph or not. And based on that, we insert edges based on each entry in the edges.txt file. And then we have two functions down here which act as wrapper functions for the shortest path and the landmark path, which are two algorithms that we've implemented, which we'll talk about a little bit later.
Okay, so for our traversal algorithm, we decided to go with BFS, which is a breadth first search. And our algorithm for BFS essentially takes in a vertex, which is called search here, and returns true if the vertex exists inside of our graph structure, and returns false if it's not found. So in order to implement this algorithm, we essentially used a map in order to keep track of which vertexes have been visited and which haven't been. And as you can see here in the first two for loops, they're just enhanced for loops that initialize the initial statuses of the vertexes or vertices and the edges. As you can see, the map, we're initializing it with false, every vertex and every edge we're initializing it with unexplored. And in the final for loop, that's the algorithm that actually calls on the helper function BFS, which we implemented to actually do the searching part of the algorithm. And by using this enhanced for loop, it can reach every part of the graph, even unconnected ones on different components of the graph. And so if we scroll down a little bit to the helper function, so essentially if the vertex is unexplored, then it will call BFS on that vertex. And we're not using the recursive implementation, so we're using the queue and the while loop, as you can see. And so for the first vertex, you just set it to true for visited, and you just add it. to the queue, and then during the while loop, you pop the vertex off the front of the queue, and then we create a vector, as you can see, to get all of the adjacent vertices to that vertex. And we parse through every single vertex in the adjacency vector, and we check if the vector has been visited, and if it hasn't been visited, if the search vertex is equal to the one that we're parsing through, then we set that to true and we return it. And if it's not, then we set the edge to discovery and we set the visited to true. And then you parse through every adjacent vertex until the queue's empty. And yeah, that's BFS.
So the algorithm that we use to actually find the shortest distance from one vertex to another is Dijkstra's algorithm. And the way we actually do this, or our implementation, takes in a source vertex and returns a map. This map contains every single vertex on the graph as keys, and then the value is a pair containing an integer, which represents the distance from the source to that vertex, and another vertex, which represents the preceding node on the path to that vertex. So I won't go into too much detail about about this method, but the gist of Dijkstra's is we start at the source vertex, and then we traverse through every single node on the graph, adding the weights of the current vertex that you're on onto the edge that you just traveled onto. And then if that weight is lower than the current minimum on the map that you have, then you update it and you set that previous node to the preceding node on the vertex. That way, when you're finished traversing through the entire graph, your map contains the shortest path or the shortest distance from the source node to every other node on the vertex or on the graph. So the shortest path algorithm that we implemented takes in a source and a destination vertex, and then returns a vector representing the shortest path from the source to the destination. In order to do this, we first call Dijkstra's algorithm on the source. And since Dijkstra's algorithm returns a map that contains the preceding node of every single vertex on the shortest path to that vertex, we can backtrack through that map from any other vertex on the map to get the shortest path from the source to the destination.
Okay, so the algorithm I implemented was landmark path. It's really simple. Basically, landmark path, you're given a source and a destination, but there's also a stop. And basically, this algorithm tries to find the shortest path from the source to the stop and to the destination. The stop is also known as the landmark, hence landmark path. So basically what I did was first I used Dijkstra's algorithm to find the shortest path from the stop to the destination and added that to my current path. That's what the while loop is doing. I'm inserting the path. And then I did the exact same thing for the source to the stop, which is the second part, and map that again to the path. Then I return it.
Okay, so our project gives users two options when they're determining what path to take, either a shortest path or a landmark path. And so we're gonna start with the shortest path. And say we wanted to go from Eikenberry to the South Quad. We'd input these as the starting and ending points. And our project outputs what bus line to take and from what stops and what intermediate stops to take as well. So say, for example, we had maybe a path that doesn't exist in our current data set. So we'll take the Cersei to Crystal Lake Park. Our program is able to identify that we either have 0 nodes in our path or 1 node in our path, and so no such route exists. And so, say for example, we wanted to run a landmark path. We're able to input a starting point. So we'll start with ISR, and say we wanted to visit Cranert Center. So we're going to input that as well. And if we wanted to end up at the Cersei, we'll input that. And our program is able to tell us each path and the bus routes. And so we're going to take ISR to Cranert Center, which is our landmark, and then our landmark Cranert Center to the CERC, which is our final destination. So through this, we're able to tell the user what route to take and for how long in order to get from point A to point B.